And that's the bottom line. And so our whole mantra, if you will, is, people say, well, how much is the oil going to cost? At this point, to me, it doesn't matter as long as we're cost competitive with other fuel sources.
Right. But in your research, or perhaps in your goals from the beginning of the process to having the oil at the end, or even the fuel at the end, you've gone through, if you're trying to make biodiesel, you've gone through transesterification. You have your biodiesel product, you can put it in the tank.
There has to be an energy balance there all the way across. Yeah.
What sort of price, and I know this sort of floats around in a bubble, it could change depending on a lot of different parameters, but ideally or as a goal, what are you shooting for a gallon of biodiesel? It's hard to say.
Yeah, it's very difficult.
But
I'm not going to put a number on.
That's fine. Suffice to say, you want to remain competitive.
Yeah, that's all it boils down to. As long as we can be competitive, we can sell all of what we can make.
And not just competitive, considering that oil may go up to $70, $80, $90, $100 per barrel.
What was it last week? $90 a barrel.
Yeah, it keeps fluctuating, but as it is, I think you're just looking to remain competitive, which is really good. Looking at these strains that you're developing, or the ones that you're screening, can you actually identify some of the strains that you've already screened, ones that you're ready to plug into a system, and maybe talk about the sort of parameters that would make these strains ideal? Or you have a strain for certain geographical areas or climates?
One of the reasons that we're approaching this with, from the standpoint of using indigenous species rather than a GM organism, is that Mother Nature's done a pretty good job of balancing things out. I can go anywhere in the world and collect algae. It's everywhere. We know there's between 60 65,000 identified species at this point. Those of us that work with algae think there's another million out there that haven't been identified. I mean, if you start to think about that, there's been about 3 species of algae that have actually been what we consider domesticated, so they're used on a regular basis, and we understand enough of them to look at this. But by going out into a local area, let's say if you wanted to put a unit in New York, okay, your conditions here are considerably different than what you're going to find in El Paso, Texas. But if you come here and collect local samples of water and start looking at the algae is designed to grow in these conditions. So it fits the environment, okay? They may grow a little slower, they may grow a little faster. Some of the cold water species of algae actually produce more oil than some of the more tropical species of algae do. So it's finding that balance, okay?
And in your systems, there seems to be a propensity or a really great opportunity to co-house or co-site these modules with industry, with agriculture, in that you can either use some of the nutrients that are considered waste products or waste streams, or you can sequester, again, stack emissions, be it carbon dioxide, or maybe a more complex mixture of gases from the industry, so that instead of having them just go out into the atmosphere and contribute to global warming.
Well, for example, if we're taking stack emissions and we've scrubbed it out and we've got good clean CO2 coming out of there, and we start pumping that in at very high levels into the system, well, we typically see about a 20% increase in growth rate of the algae with the addition of external CO2 rather than atmospheric.
So all of a sudden something that is considered deleterious and harmful,
now it's useful.
Now it's something good.
The reality is, though, and I think this is important to understand, if that CO2 goes up in the atmosphere, I'm still going to get it, okay? So it doesn't matter whether I'm taking it off the flue stack or if I'm just pulling it out of the atmosphere.
So the CO2 is not going to get away from you.
The CO2 is not going to get away from me, okay?
Excellent. And also in your structures, there's the potential to strap on solar panels, hook up with geothermal energy.
We use geothermal now for both heating and cooling of the process. My long-term goal is to get this completely off the grid. Mm-hmm. Between wind, solar, and geothermal, we hope to get it completely off the grid.
So what you would be talking about as well, we've talked about large-scale installations, but seeing as how this is modular, this is something that could be broken down into quarter-acre, 5-acre installations, which would be easier to get off the grid, would be more economically viable for small-scale production systems, and might be something that's attractive to either your, organic farmer or somebody who has a small industry that also wants to sort of diversify their product.
We see a great opportunity to go into actually the urban environment, okay? work with the cities, okay, to help reduce their carbon footprint and supply them with a fuel source for their transportation needs on an urban environment setting.
And a lot of the materials that we're talking about in these systems don't seem too specialized. Like a lot of what we're talking about in terms of our build-out is plastic. You're talking about a sort of armature that's holding these bioreactors and moving them along. So it doesn't sound like there's anything too special. It's a lot of off-the-shelf
A lot of it's off-the-shelf, yeah. The reactors are probably the most complicated part of that, and that's something that we're manufacturing. So.
And in terms of the actual physics of these systems, I know there's a little bit of chatter online where people are saying, well, these things are spaced so close together, how do they get enough light to penetrate through? They can only get light on one side. Can you perhaps speak to those issues?
That's one of the probably one of the more interesting conversations that goes on. We have what I consider to be black box thinkers, okay? And if you look at physics says that on a given surface of land, there's so much solar radiation going to hit that at any given moment. Okay? And if you take a traditional higher vascular plant and you look at photosynthetic conversion, you can only convert a certain percentage, usually between 8 and 15% of that light into usable energy, okay, through the process of photosynthesis. By going vertical and dynamic, we're not exposing one cell with one amount of chlorophyll in it. We're exposing trillions of cells, okay? And we're doing this very large volume. And by doing that and going vertical, we're able to absorb more of the solar radiation that's hitting this one particular square. It doesn't quite fit the physics of a black box, okay? But it works.
Right.
Algae is unique as one of the more primitive organisms. It uses energy at all different levels. Okay, it will absorb energy at a much wider range. Okay, to sustain itself than a traditional higher vascular plant will. So that's why we went vertical. That's why we stacked them as close as we do. We want to capture as much of as many photons as we can.
So the end lesson or the end phrase that can conceptualize this is go vertical.
Absolutely.
It's a great name for your Vertigro. I think it's a great double entendre. You know, we're not only talking about being vertical, but vert green.
Exactly.
Very smart. I don't know who's in your marketing department, but they've got to figure it out. And that is one of the points, and I think that's one thing that separates you from not only a lot of the companies that are working right now, but the previous literature, the previous research was done on either open pools or closed pools, and one of the problems was the algae at the surface received all the radiation.
Exactly.
You know, they grew just fine, but even a couple of inches below, the algae
just nothing there.
There's nothing there, and they don't develop any oil, any lipids. They mostly eat carbohydrate, protein, things like that. But there's competition because of that surface area. So one of the points is expand your surface area,
and you're going to absorb more light. It's that simple.
Very smart, very smart. Well, I wish you the best of luck, and I want to thank you for coming by. This has been a great conversation.
I've really enjoyed it. Thank you very much.
And I'll be looking for you in the future.
Good deal.
Thanks a lot, Glenn. Glenn Kurtz, Valcent, they've got Vertigro coming online soon, and we'll be looking for their test results from all their trials in the near future. When can we expect to hear more from you?
Probably mid-2008.
Mid-2008. We'll be looking for it. Thank you.
What we have is a closed-loop photobioreactor. So our goal is to produce the greatest amount of biomass from algae that we can. And by going vertical, we believe that we can increase the yield by increasing the surface area and the volume of material that get exposed to sunlight. So we have a system that continually recycles, so it's a dynamic system in a closed loop. So algae goes down and starts out in a tank, gets picked up by a pump, goes up into the reactors, and then gravity takes control, moves it through the reactors, they get exposed to sunlight, go back into the tank, and the cycle is repeated over and over again. I know that algae is the fastest organism, fastest growing plant on the planet, and it sequesters the greatest amount of carbon dioxide. But at the same time, it produces lipids, basically vegetable oil, and a lot of it. So if you look at a single cell of algae in the right species, as much as 50% of its body weight is a high-grade vegetable oil. So while we're sequestering carbon dioxide, we're also producing these high-grade lipids that can be used for a variety of purposes. The beauty of algae is the fact that we can actually be selective about what carbon chains are coming out of it. So for example, if you want to make jet fuel, we can give you a strain of algae that's going to make the carbon chains that are necessary to manufacture jet fuel much more efficiently than you can any other crop. Or if you want to make diesel for a truck, we can give you the carbon chains that are ideal for that. So we can tailor the lipids based on the species of algae that we're growing. If I grow an acre of corn, and I'm looking at it from the standpoint of producing oil, I can grow about 18 gallons of oil per acre per year. So now I'll move up, let's go up to the next highest, or what's the most prevalent, is palm. Palm, we get 700 to 800 gallons per acre per year.